and welcome back to Rosie's STEM. Today we're going to be talking about how to do linear regression using Python. So we're going to talk about both simple and multiple linear regression and do a few examples as well. I will have a GitHub repository linked down below where you can find the notebook that I use for these examples. So please go ahead and grab that and code along with me. I'm going to show you two different modules for doing linear regression. They're called Sklearn and Statsmodels. If you don't already have those installed, please go ahead and either pip install them or use Anaconda, whatever your package manager is. And although there are other packages, those are the ones that I see most often, and they represent two kind of purposes of linear regression, which really are prediction. So using some information to predict an outcome. So if I know that my house is 300 square feet, can I predict what the selling price of the house should be? And then understanding relationships. So maybe I'm not so interested in predicting the sale price of the house, but I want to understand how square footage is related to price. And I would say that Sklearn takes more of that machine learning prediction side of things, makes that easier. And Statsmodels takes more of that statistical side, that understanding of relationships. You'll see a lot of computer scientists use Sklearn and more statisticians use Statsmodels. And yes, I did use the term machine learning. Regression is a type of machine learning. Linear regression is one of the most simple types of machine learning. Apologies if you can hear my dog chewing on her bone underneath the desk. She has decided that she wants to join the lesson. And we can go over much more complicated regression models or machine learning models in general in future videos if you'd like. Let me know down below which ones you'd like to see so I can prioritize those. But I want to go ahead and hop into Python. All right, so we're opening this up in Google Colab. And one of the first things you need to do when you're in Colab is make sure that you have your data uploaded. Because we are working on the internet. It doesn't necessarily have access to the directories on your computer unless you tell it to. So here, I'm just going to make sure that I have my data set here, which I do. I uploaded it. What I did was I clicked here and then clicked on the file that I wanted. So now it's available to me. All right, so as a reminder, the main purpose of linear regression is to both predict things and to understand relationships. So sometimes we're more focused on one than the other, but in essence, linear regression helps us find and describe linear relationships between variables. And that linear part is very important because there's other models we can use to describe other types of relationships. But for this example, we're going to be looking at linear relationships in the Palmer penguins data set. It contains measurements for 3 species of penguins across multiple islands in Antarctica. So researchers would find the penguins and then take a few measurements. Some information about those measurements is here as well. And we're going to be trying to predict the body mass in grams of the penguins by using some of the other features. The first thing that I want to do is have you guys just look at the data. So I'm actually going to comment this part out for now. And when I run this, you can see that the first 5 rows of the data pop up. That is the head of the data. What I'm using to load in and display the data here is this pandas library. Pandas is like a really important library in data science. I'm also using NumPy and Matplotlib. If you're not familiar with these and you want videos explaining them, please let me know. But for this video, I'm gonna assume that you know how to work with pandas and how to get data into Python. So you can see species, islands, Kalman length in millimeters, Kalman depth in millimeters, the flipper length, body mass, and then sex. And you can also see that there are some missing values. That's what this MAN here is. So what that means is the researcher found the penguin on the island, but for some reason they weren't able to take measurements of that penguin. Maybe it got away. They weren't able to like catch it or properly take measurements for some reason. So since there are some missing values, I'm going to go ahead and drop those just for ease for this example here. But what you might want to do in real life is you would impute those in some way. So here I'm dropping some missing values. And you can see most of the missing values were the sex of the penguin, but we do have a few missing values in other things. And the very first model that I want to make is a simple linear regression model. So we're going to start by just using one predictor variable to try to predict the body mass of a penguin. And we're going to focus on the culmen length. And if you, like me, are not very familiar with penguins or birds in general, the culmen length is actually the length of the ridge along the top of a bird's bill. So this is its culmen. And the length is how long that is in this direction. And then the depth is like how deep or like wide their beak is in this way. This image comes from Alison Horst. There is a link here where you can see a lot of the art that she made specifically for this Palmer Penguins data set. So I highly recommend if you're interested, look at that. So let's go ahead and get to the modeling. In order to model this, we need to actually import the modules that we're going to use, which I mentioned before. Those are scikit-learn and Statsmodels. So scikit-learn is abbreviated, so scikit-learn is abbreviated sklearn. And the portion of sklearn that we're going to be mostly working in is this linear model section. And within that linear model section, there is a function called linear regression. So we're going to, from that section of scikit-learn, import the linear regression function. We're also going to need a few other things just to be able to play around with the model. And so the first is this train test split function from model selection. And the second is this function that will calculate the mean squared error, and that comes out of the metrics section. Then when we use Statsmodels, we're going to need some functions from the Statsmodels API. So statsmodels.api, we're going to import, and we're just going to give it the alias SM for Statsmodels, so we don't have to type that whole thing out. First, we need to know what features we're using and what target we're going to use, which we already decided our target is body mass, and our feature is going to be culmen length. And we need our feature to actually be in this like 2D array-like object that sort of looks like a data frame. So I'm going to use this double bracket syntax, which makes sure the data is pulled out as like a data frame or as a 2D array. And it's only going to grab out this one column from the penguins data set, which is culmen length in millimeters. For the target, or like what we're trying to predict, I don't need to use that double bracket because it knows it's just going to be one column. So it just wants it as like a 1D array. So here I just pulled out the column like you would normally do in pandas. And the next thing I do is split my data into a training and a testing set. This is something we commonly do in machine learning, and it allows us to build a model and then also see how well that model works on data it hasn't seen before. So this train test split function will take in your X and your Y, so your features and your response that you're trying to predict. And if you give it how much of your data you want left out for testing, it will split it into a training and a testing set for you so that you can build your model and then also play around with it and see how well it works. And this random state piece is just setting what's called a random seed, which means that it'll randomly sample it. But since I have this random state set, if you run this same code with the same random state, you'll get the exact same random split that I got. It's sort of where your random number generator starts. So let's build the scikit-learn model. The syntax to do that is we first have to create a linear regression object. So we have to tell scikit-learn that we're wanting to do linear regression. So here I'm just instantiating the object by running the function linear regression. I don't have to give it any input. And I'm naming that object regr for regression, simple sk for sklearn. And then I'm going to use the .fit method, which is part of this linear regression object. It has this method. And what it does is it's going to fit our regression line. So it's going to use some of the methods that we talked about in our simple linear regression video. It's going to do it much faster than I would be able to do it by hand. And it's going to take that data and draw the best fitting line through the cloud of points. So here I just ran .fit, and we've now trained our model. To see how well that model works, I can use the .predict method. And what that does is it takes the line, takes a bunch of points from our x's that we left out, right? Because we have our x train here. This is our training group, our x test, our y train, and our y test. So for our training, when we fit it, we use both training x and training y. And for our prediction, we're going to give it the x test, so the points it hasn't seen before, and we're going to see how well it can predict those and kind of compare what we get from our line to the actual values in the data. So here, we are saving those as ypred simple sk. These are our predicted y's. I'm going to print out our coefficient and intercept. So think y equals mx plus b. This is the m and the b. I'm also going to calculate this mean squared error between our predicted y and the true y in our data. So what that's going to do, if you think back to the first regression video, we talked about mean squared error. It's going to look at the difference, like those residuals between the y's, the predicted ones on our line, and the actual real data. It's going to square them, add them together, and take the average, right? So it's sounding very similar to things we were doing for least squares method. And for now, I'm just going to go ahead and comment out the rest of this so that we can see it printed out some results here. So we printed the coefficient, so the coefficient and the intercept. This would be like our m and our b, and y equals mx plus b. And then also the mean squared error here on our testing data. And you can see that we got 90.5, 223.6, and then a mean squared error of about 443,000, which looks really big, but remember we're talking about housing prices, so these numbers are just naturally going to be bigger. And we can put together this coefficient and intercept into an actual line format. So we would have y equals 90.57x plus 223.6, and that would be our best fit line, our linear regression line. And what happens when we use this .predict up here, so this here, is it takes these x test values and it plugs them in for x in that line and comes up with some y values. And those are our predictions. That's our ypred. And when we compare those against the actual y values from our data, that's how we get our mean squared error. And really for mean squared error, we use it most of the time for comparing different models to each other. So we can try different predictors and see which one gives the smallest mean squared error. So which one has y's that are closer to the true y's. And that's usually the model that we would want to pick. But right now we just have the one model, we just have the one metric that we're looking at. And what I want to show you is how we can build that same model, but using the Statsmodels module. I'm going to go ahead and uncomment this piece out. And we still have our x train, x test, right? Same data from up here. Our y train, y test as well. Now we're going to be using this statsmodels.api module, and we have alias that as sm, and there is this function inside Statsmodels called add constant. And the reason that we would use add constant is that by default, scikit-learn knew we wanted an intercept in our model. It knew that we didn't just want mx, we wanted mx plus b. Well, people don't always want that intercept. Sometimes they don't. And Statsmodels by default does not give you that intercept. So if you want it, you have to use this add constant function. And I do want this intercept, and I'm going to want it when I'm using my x train and my x test. So I need to add it to both. So here I've just gone and used add constant to add that to both here. And then I can actually create the model. And here I called it an OLS model for ordinary least squares. And you can use the OLS function in Statsmodels to actually create the model. And notice here I'm using my training X and my training Y, not the testing data, just like I did for scikit-learn up here when I fit the model. But you should notice that when you fit things for scikit-learn, you have to give X first, Y second, and it's the opposite for Statsmodels. You have to give Y first, X second, because, people like to make things complicated. And then we actually fit the model. And in scikit-learn, when you first build the model, you don't give the data, but when you fit it, you do. The opposite for Statsmodels. So now when we fit it, we don't need to give the data because it already knows what the data is. We gave it to it earlier. And this is just going to go ahead and calculate that coefficient and that intercept. And then we can print the summary of results. The nice thing about Statsmodels is it gives us this full model summary with everything together, so we don't have to ask for things individually like we had to do for scikit-learn. We can still make predictions on a testing set, so we can use .predict. The Statsmodels module also has a .predict method, and here we give it our X test. This is the same data that we gave for .predict right here. And then I'll also calculate the mean squared error so we can see how it works for Statsmodels, similar to scikit-learn. I'm just going to rerun this whole cell. And it should print out everything. So first we have our scikit-learn information that we had before. Notice that it doesn't change based on rerunning this cell. The only thing that might change when you rerun it would be this if we hadn't set a random state, right? Because it would give us a different random split of the data. But since we set a random state here, it's going to give us the same random split each time. So every time we run this, we should get the same thing because there is a nice closed form solution for ordinary least squares. There is a best possible coefficient and intercept. We don't have to estimate it. And then this piece right here is our Statsmodels simple regression summary. And it gives us a lot of information here, some of which we probably don't need. The things that we are going to recognize, we see this coef right here. These are our coefficients. Here for constant, C-O-N-S-T, const stands for constant. This is our intercept. So you can see it's 223.622, which matches what we got up here from scikit-learn. And here we have our coefficient for Coleman length, which is our coefficient here, this 90.5694, they also match. The other thing it gives us is a measure of standard error for each of these, so a variance. It gives us t, which is a t-statistic, if you know anything about t-testing. And it gives us a p-value as well as a confidence interval, so a 95% confidence interval. And if you want to know more about p-values, I do have a video on that as well. We can go through hypothesis testing separately. But in general, what this is doing is it's running a hypothesis test. And what it's trying to test is, are these coefficients significantly different from zero? So do these variables have an important place in this regression line? Or maybe not. And since this is significant, it means that this is significantly different from zero, enough that we can say Coleman length does help us predict the body size of a penguin. And this is a confidence interval around this estimate. So we can say 95% of intervals that we might create like this would include the true coefficient for Coleman length. And this confidence interval goes between 76 and 105. That's pretty far away from zero, which means that it's very unlikely that the true coefficient for Coleman length is zero. So Coleman length is probably somewhat important in this line, right? It's probably not going to drop out by being multiplied by zero. Instead, we're multiplying it by around 90. There's a lot of other information down here that we can get into in other videos if you want, but the rest of the important information is really up here. So you can see this where it says R squared and adjusted R squared. The adjusted R squared is usually the more important one to look at, but if we're doing simple linear regression where we only have one variable, you can look at the R squared as well. And what these tell you is the proportion of variability in our body mass that is explained by the variables in our model. So we can explain about 36% of the variability in body size using Coleman length. All right? 36% isn't that much, but the fact that we're only using one variable means that it is pretty useful. And maybe if we added some additional variables, we could get it even better. Ideally, we want our R squared as close to 1 as possible. We want to be explaining as much of the variability in our data as possible. That means that we're modeling it well. The lower it is, the less good our model is going to be at predicting new values that it sees. And we also printed out here the mean squared error for our stats models model. And you can see that it is the same as the mean squared error from scikit-learn, right? Because we made the same model. It's the same regression line. We're just using two different modules, so I can kind of show you the pros and cons of using each and the type of information you get with each. In general, if you're focusing mostly on prediction, scikit-learn is pretty easy to use. But if you want to be able to really interpret some of these coefficients, if you want things like these significant tests, like these p-values, so you can tell how useful some of the coefficients are, Statsmodels is nice because it gives it all to you in one big output here, in one big summary. So it really depends on what you're trying to do. And here we can visualize this simple linear regression model with a plot so you can kind of see what's going on. So this is our data. This is Coleman length versus body mass. And you can kind of see there is a spread, but there does seem to be a linear relationship in general. And usually I would suggest my students start by plotting the data to make sure there's a linear relationship. But we knew we were going to start with linear regression here. And then I plotted the regression line from scikit-learn and Statsmodels, and you can see they're right on top of each other. So scikit-learn is this solid blue line, and the dashed red line for the Statsmodels model is right above it, like right on top of it. So they gave us the same line, which is good. It means we're doing things right. They should give us the same line. But we saw here, using this R squared, that it was only explaining about 36% of the variability. We can probably do better if we create a more complicated model. For example, if we add more variables into our model. So let's play around with that. To do that, we need a multiple linear regression model. So I'm going to go ahead and build one that doesn't just include Coleman length, but it also includes Coleman depth, flipper length, and that's 3 different features now. So we now have 4 total variables. This is going to be 4-dimensional. So I can't really plot it quite as easily as I could plot this 2-dimensional model. But you can see that we actually build the model really, really similarly to what we did for simple linear regression. Now, instead of just grabbing out one feature here, just grabbing out Coleman length, or grabbing out all 3 features, I've just kind of separated it out to make this line a little bit shorter. But this is a full array. Think of taking this big piece and plugging it in where this says features multi. There's still going to be double brackets, right? Still going to give us a 2D array-like object, like a data frame. And then this Y stays the same. We're still just predicting body mass in grams. That's going to be our target. We always have one target for linear regression. I'm going to do my train test split here. I'm using the same random state and the same test size as before, but these are things you can always play around with. So I'm taking 20% of my data to be in my test set, which means 80% is in my training set. It's a really common split to use. Sometimes people will also use like 30-70 split. Those are the more common ones that you'll see. And for our scikit-learn model, which is this piece right here, we have this part where we are building our linear regression model. We're instantiating it. So starting it out, getting ready to fit it. And for scikit-learn, we have to run this .fit method with the data that we're going to use to fit it. So that's our training data. We give X first, then Y. No, we don't have to like save this into any variable. We've already instantiated a model. This model exists. We're just now saying fit the model and actually calculate those coefficients for us, please. And then once it's fit, we can use .predict to get predictions out. So we use .predict, we give it the X. That's the X that's going to be plugged into our equation. And here we do save this somewhere because we want to take those predictions and save them in an object so we can kind of calculate error later. I'm going to go ahead and print out these coefficients. So coef is going to give us the coefficients for all of the features that we've included in the order that we included them. So we're going to get 3 coefficients. The first for Coleman length, then Coleman depth, then flipper length. Intercept is always given separately. And then I'm calculating the mean squared error again. We're going to see if we can get a lower mean squared error for this. Remember, lower mean squared error is better, higher R squared is better. Let's comment out the stats model stuff for now and run this. And you can see we do have 3 coefficients here. Note that this first one is not 90 anymore, right? Coleman length before was 90. It's no longer 90. Now that there's more things involved in the model, it's not giving that one as high of a coefficient, probably not giving it quite as much weight because it can kind of spread it out between other features. The Coleman length and depth and flipper size might all be related to each other as well. So it's going to kind of split that effect across. And the intercept is also different. Notice it's now negative too. And our mean squared error here is 137,600, which if we compare to what we had up here, it was 443,075, so it's much lower, right? We have much less error here in this one. And it would be useful for us to know the R squared as well. There are functions we can use to calculate it using scikit-learn, but let's go ahead and just run the stats model as well so you can see how we would do it, and we'll get an R squared that way. All right, so I'm going to rerun this. What we've done here is we have to first add our constant. We have to use that dot add constant. That's going to make sure that we have an intercept in our model. We have to make sure we add it to both our training and our testing X, so it knows there's going to be an intercept in both. Then we create our OLS model. When we create our OLS model, we do need to give it the data for Statsmodels, even though we didn't have to do that for Sklearn. And the Y goes first. Then we fit it. And note, this time we are saving it to an object, giving it a variable name. We didn't have to do that with sklearn. There's subtle differences in the syntax here. And then I'm going to print out the summary. I'm going to get some predictions using .predict, saving those, and then get the mean squared error so we can double check we did everything right. Because if we did it right, they should be the same. The mean squared error from Statsmodels and scikit-learn. So we already ran this. So we can look down here at our mean squared error at the bottom. They do look the same. That's good. And here's our summary. So we have our constant here. This is our intercept. This looks the same as the intercept from up here. If we look at our 3 coefficients, those also look the same. So everything's looking good at the moment. We can look at the p-values. So the constant is significant. That's not really important to us. What we want to know is, are these different variables, these features we're using, useful? It looks like the Coleman length and depth do not have p-values less than 0.05, so we would not consider these statistically significant. But flipper length is statistically significant here. It does have a p-value less than 0.05. So it looks like flipper length is the more important variable for understanding the weight of a penguin. And when I'm thinking about that, it kind of makes sense. Bigger penguins are going to have bigger flippers, but penguins might have longer, short beaks, right? So it makes sense that this might be a little bit more important, especially if you're thinking about like baby versus adult penguins. But I'm not really a penguin expert. The other thing that I really want to point out is here's our R squared. And whenever we're doing multiple linear regression, we want to focus on this adjusted R squared. And that's because mathematically, with the way you calculate R squared, if you add more variables to a model, more features, your R squared is always going to increase. So it's not really a good way of seeing if the variables that you added actually are helping your model. But the adjusted R squared won't. It kind of takes that into account. It fixes that problem for multiple linear regression. So we look at our adjusted R squared, and it's like 76, which means 76% of the variability in our data. So when I'm talking about variability in data, I'm talking about like the spread of points, although it's no longer in this 2D space, it's in a 4-dimensional space, right? 76% of the variation in that spread, or how they are spread out, is explained by our model. So we're able to explain quite a bit of that variability, right? 76, much closer to 100% than our 36 from before was. So this model is better at capturing what's going on with the body size or body mass of a penguin. So let's compare these models. I'm going to compare the mean squared error as well as the R squared. Gives us a nice little summary. You can see how our mean squared error went down. You can see how our R squared went down. This one is a lot harder to picture by showing you like a line in an image, right? Because we're now in 4D space and it would be a hyperplane. But when we get into these multiple linear regression models, we usually focus more on these metrics and look at these metrics instead. And if you do pull this notebook down off of GitHub, you can kind of play around with some other variables as well. There are variables in here that are not necessarily continuous numeric variables. Remember, I said we were going to only focus on continuous numeric variables for this video. You can include variables in your model that are categorical, right? That are not necessarily continuous numeric. We just have to do a little bit of extra data cleaning and know a little bit more about linear regression to understand how those work. I'm happy to make a video about that as well. I also would like to make another one about checking linear regression assumptions. So we want to actually make sure that the models that we're building are right for the data that we have. Linear regression isn't the right model for every data set. Remember, we were looking at this graph up here, and it does look like there's a linear trend. That's not always true, and there's different types of data that won't necessarily work as well with linear regression. So you have to check to make sure that you're meeting all of the assumptions that are necessary to do linear regression. There's also different regularization techniques that we can play around with for linear regression and other regression models. And there's a lot of other regression algorithms out there, especially when we're talking about the entire realm of machine learning. So these are all things that are areas for further exploration that I would love to make more videos about. If these are things that you're interested in, please put a red heart if you would like to see a video about categorical features, a blue heart if you would like to see a video checking for assumptions, yellow for regularization, and green for other regression algorithms, and I'll use that to prioritize the order to make the videos in. All right, thank you guys so much for watching. I hope that you enjoyed the video and that you learned something. If you did, please let me know down below and give this video a like. If there are things you would like to see in future videos, please also let me know that in the comments, and I would be happy to make videos based on what you guys want to see. Also, go ahead and hit subscribe if you haven't already. It really helps out my channel, and I will see you on the next one.